In this section, we want to look in more detail at transformations. In a previous section, we changed from rectangular coordinates to polar coordinates. We first took a look at the region described by the rectangular coordinates and decided how we would describe that in polar coordinates. Then we converted the integrand from rectangular to polar coordinates. And finally, there was another factor which we explained as being part of the definition of polar coordinates. Likewise, in triple integrals, we took a triple integral in rectangular coordinates, converted it to spherical coordinates by converting the region from rectangular to spherical, converting the integrand from rectangular to spherical, and then there was another factor which again we got from the way we designed the integral from the spherical coordinate system. Now, in general, we can have any transformation that maps or changes a region from one plane to another plane. For example, we're going to take this square that's in the UV plane, and we're going to convert that using a transformation. So our transformation is we're going to let x be u times v and y be u squared minus v squared. So according to that transformation, I've got this color-coded so we can see what is happening to the boundaries. So first off, we have the side of the square u equals 0. That would be the green or left side. And substituting a 0, we get y equals negative something. Well, y equals negative something is simply the negative y-axis. If we take u equals 1, that would be the right side of that square. Plug 1 into both equations for u, then we get the parabola y equals 1 minus x squared. If we take the v equals 1, that was at the top of the square, we get the parabola y equals x squared minus 1. If we take v equals 0, the bottom line of the region, we get y equals u squared, or y as a positive. So we have this square that is mapped onto this region. Now, two kinds of transformations that are quite common in mathematics are linear transformations, things that just replace x's and y's with some linear equations involving u's and v's. And we have rotations about the origin, which takes a region and, as you can see, changes it to another region that is simply twisted or rotated about the origin. Now what we want to do here is learn about the Jacobian. The Jacobian is a matrix involving the partial derivatives. I'll show you where that comes from. Now if we write our transformation in matrix form, we can use the curve u, that's the boldface u, to represent a curve in the UV plane, and it's a vector valued function consisting of the u's and the v's as functions of t's. And so we have the vector function x of t being the transformation of the curve in the uv plane to a curve in the xy plane. And so here's the derivative of x by the chain rule. We do the derivative of x with respect to u times the derivative of u with respect to t, derivative of x with respect to v, times the derivative of v with respect to t, and so on. That can be rewritten as the matrix containing the partial derivatives and the matrix containing the derivative of u with respect to t and derivative of v with respect to t, which we can write kind of compactly as the Jacobian of the determinant and the derivative of u. So this is kind of like having the derivative of the transformation. Now the Jacobian simply maps tangent vectors from curves in the UV plane to tangent vectors and curves to the XY plane. Back in Calculus 1, we learned the substitution method. If we had an integral involving x, we could change that using what we called a u substitution. We would let u be some function of x, and then we would convert our integral into one that had a different function, this time of u, different limits on the integral, and some other factor. So in double integrals, if we change from one system to another, for example, when we changed to polars, we had a transformation whereby we changed our region into the new region. We changed our integrand into the new variables, and there is some other factor. That factor is our Jacobian that we're learning about. In triple integrals, when we converted from one system to another, we transformed the region, we transformed the integrand, and then we had another factor. We just kind of remembered what those were for certain other transformations like spherical and cylindrical coordinates. But that again is our Jacobian. Now to see how this Jacobian works, we're going to do a change of variables or a transformation. Here's a region that we're asked to integrate over. Region is bounded by the line y equals x, the line y equals 3x, and the line x plus y equals 4. As you can see, this region is neither type 1 nor type 2. It's neither x simple nor y simple. Hence, we'd have to use several integrals to do that. However, let's see how we could transform this with a substitution. So we're going to start by taking the line y equals x and using this transformation, we're going to see what would that change into. And so substituting u plus v for y and u minus v for x, we get v equals 0. So in this graph, here's the line v equals 0. Notice how it's color-coded to match the one on the left. So y equals x is transformed into v equals 0. Likewise, y equals 3x, by plugging in the values of y and x, we come up with v equals 1/2 u, which is the green line, and plugging in u minus v for x, u plus v for y, we get the line u equals 2. And so the region originally that was like this is transformed into this region. Now if we're going to change that integral, then we're going to need the Jacobian, which here's the definition of our Jacobian matrix. We need to take the x, which is u minus v, the first component listed in the transformation. We need to do the partial of that with respect to u, which would be a 1, the partial with respect to v, which would be a negative 1. We need to take the y, do the partial with respect to u and v, and then substitute those into the Jacobian matrix and do the determinant of that. Now to evaluate this determinant, remember we multiply, and subtract. So that'd be 1 minus negative 1, or 2. And so the integral then would look like this. Our x is u minus v, y is u plus v, so we substitute the x and the y. We have the Jacobian, and then the region that we describe in the UV plane would be v going from 0 to u divided by 2, and u going from 0 to 2. Now, once upon a time, we transformed rectangular to cylindrical coordinates, and we changed integrals from rectangular to cylindrical. Let's take a look at that transformation in a little bit more detail. The transformation was x equals r cosine theta, and y equals r sine theta, and z equals z. Let's find the partial of each of those. The partial of x with respect to r, the partial of x with respect to theta, and the partial of x with respect to z. Partial of y with respect to r, y with respect to theta, y with respect to z. Z with respect to r, z with respect to theta, and z with respect to z. We'll set that up in a determinant and then evaluate the determinant. Now, I'm not going to spend time on this PowerPoint going through the mechanical details, but here's expanding by the first row and simplifying. And sure enough, we come out with the factor r for our Jacobian determinant. Hence, when we change an integral from rectangular to polar coordinates, there is a factor of r. Now, we're going to take the region that is bounded by x equals y squared minus 4, and x equals 9 minus y squared, and x equals 16 minus y squared. I've got them all color-coded. And we want to find that region. So the region that we're integrating over is this region. That is neither type 1 nor type 2. So we're going to do a transformation on that. So here is another way of writing those equations. Notice how the first two both have an x minus y squared and the next two both have an x plus y squared. So it seems natural that we might do a substitution. Let u be x minus y squared and v be x plus y squared. That would make us going from u equals 0 to u equals -4, v equals 9 to v equals 16, which would give us a region that looks like this. So we could change from this region into a nice rectangular region where the limits on the integral would be very easy to find. So let's see how we would go about finding the transformation of the function and the Jacobian. So here's what we've decided to use for the u and the v. Now our function, which is just a y, is needing to be transformed, so we need to know what can we replace the y with. We need to take our system of equations involving u, v, and x and y, and we need to solve that for x and y. So we will solve the system of equations using the substitution method and get x and y in terms of u's and v's. So our function, which is just a y, our integrand, would be converted into square root of v minus u over 2. Now we need the Jacobian determinant. So we'll do the partial of x with respect to u, the partial of x with respect to v, the partial of y with respect to u, and the partial of y with respect to v. Put those into a determinant and then evaluate the determinant. So then our integral looks like this. Notice that the radicals will disappear. So this transformation then changes the integral into this integral. Now that's fairly easy to evaluate.